In this tutorial, I will talk about saddle point integration and Stirling's approximation. Sometimes, or in general, in statistical mechanics, to have the idea of equilibrium properties of a system, for macroscopic system, one has to take the averages of large number of microscopic degrees of freedom. So, we have to take averages of large number of microscopic degrees of freedom. As we have seen earlier also, in statistical mechanics, usually we deal with three types of n-dependent quantities which we have to sum. First are intensive quantities like averages, such as temperature, pressure, density, etc. And they have order n to the power 0 dependence. If n is the microscopic degree of freedom and n tending to infinity we are considering. This is also called the thermodynamic limit. So, like the quantity we have discussed earlier, z, which is the summation over the microscopic degrees of freedom or the random variable in probabilistic description and divided by n. So, this quantity has order n0 dependence. Other can be extensive quantities such as total energy, volume, entropy, etc. In that case, z will be like summation over xi type of thing, and which will have a order n dependence. But you will see later, or you have seen also, in many cases there are some exponential dependencies which we have to sum. Such as quantities like this, summation over I, exponential of nxi, these kind of thing. So they have order exponential n phi type of dependence. Phi is, let's say, xi in our case. So in this tutorial we will see that how to sum this, and what is this can be simplified very much, as we have seen that the sum and averages were in earlier tutorials. We have seen these two things, and how this sum and averages of large number of microscopic quantities gets simplified because of the central limit theorem and the law of large number. So what we have seen earlier in central limit theorem, we said that this z follows, so I will write it again once. So we have seen that if there are sum over capital N number of degrees of freedom where n is tending to infinity, and if you divide by n, then also if the mean is 0, mean of these random variables are 0, that is xi average is 0, then the probability distribution of z follows Gaussian with the standard deviation sigma by root n exponential minus nx square, so z square, so z square 2 pi sigma square. But let's say if the mean is not 0, and if you consider this quantity summation I over 1 to n xi minus x average, then this quantity will also follow the same Gaussian distribution. So in statistical mechanics, central limit theorem is of great use. Microscopically, let's say you have a container of gas, which we have seen taken the example earlier also. So the gas has a bunch of little molecules hitting one, and in the boundaries of the wall they are bouncing back and forth. The molecules impart their velocities changes randomly. They impart varying forces to the wall of the container, but overall the macroscopic quantities such as pressure or total energy or center of mass of the system, we can calculate that accurately because of the central limit theorem and the law of large number. Here, before going to see how to sum these or how the sum of the exponential dependence in n gets simplified in statistical mechanics, let us have a look of the importance of taking logarithms in statistical mechanics. You have seen in many places, I am sure, that we took logarithms. So why taking logarithms are important in statistical mechanics. So normally, if let's say you have a function fx which has a minima or maxima around, let's say this function, let's say, have a minima or directly you can say extrema at x bar, then one can do the Taylor expansion of this about x bar and can neglect the higher order terms. So one can Taylor expand this x near this x bar. So f of x bar plus f prime of x at x bar, x by 1 factorial plus f prime double prime at x bar, x square by 2 factorial, and so on. And one can neglect the higher order terms since they are as we do in Taylor expansion. But let's say you have the Gaussian integral or the Gaussian function e to the power minus x square by 2 sigma square. If you expand it, what will you have? Let's say m is equals to 0 to infinity 1 over m factorial minus x square over 2 sigma square m. Is this 1 minus x square by 2 sigma square plus 1 over 2 x square by 2 sigma square whole square minus 1 over 6 quantity cube, and so on. If you want to go back to the Gaussian, you cannot neglect any of the terms. One has to take all of the terms to get back to the Gaussian again. So if one wants to go back to the Gaussian, one has to take all of the terms or one has to keep all the terms. Keep all the terms to get back to the Gaussian. However, if you take the logarithm of this quantity, log of exponential x square by 2 sigma square, then you have only one term, x square by 2 sigma square, and you can again expand it like a regular function which has a minima at some point, and you can Taylor expand it, and there will be higher order terms can be neglected. So for this pz also, so this is pz. For pz also we can do the same thing. Pz is root n over 2 pi sigma square e to the power minus x minus mu. I am saying mu, the mean, mu n over 2 sigma square. Now if we take the log of pz, then it is minus n x minus mu square over 2 sigma square plus log of n 2 pi sigma square, or minus n x minus mu square 2 sigma square plus 1 by 2 log n by 2 sigma square. So log of pz, and if you divide by n, so this independence will go away, and in the limit n tending to infinity, limit n tending to infinity, log pzn over n will be simply minus x minus mu square 2 sigma square, because limit n tending to infinity log n by n is 0. So we have seen that taking logarithms simplifies our situation, or you can write this also, limit n tending to infinity log pz, and there is no higher order terms. This is of the order of n. It's of the order of n. So there are no more higher order terms. In other words, a Gaussian. So if you have seen the plot of the Gaussian, it is something like this. This has flat near its maximum, and it has long tails. So if you expand around this maximum to have the information, or to get the information at the tails, is actually very difficult. And we have seen earlier also that the probability of finding x between mu plus sigma and mu minus sigma is almost 68%. So if you want to get the information above x, you want to let's say greater or equal to sigma, then from the peak, expanding around the peak and getting the information at the tail is actually very difficult. But if you take the, when we have taken the logarithm, the peak and tail has now on the same footing, is now on the same footing. So just taking the logarithms simplifies our situation much more, and we will see this in the saddle point approximation, or summing of the exponentials. So what we have left, that we will now derive, or we will see that how to sum the quantities which has an exponential and dependence. So now summing of exponentials. Let's say we have a quantity S which is a sum of some quantities epsilon i's. They are discrete. Let us first do the discrete case, then we will do the continuous case, where these are positive quantities and these epsilon are exponentially dependent on n. Let's say phi I is the random variable. Now let us draw it. Let's say we have these epsilon. It can take different values, but it has a maxima at some point. So this is n, this is epsilon max. Now one can always write epsilon max is less than s. S is the sum of all epsilon. So certainly epsilon x will be less than or equal to maximum and to the total sum. And if you now let's say increase the length of this up to epsilon max, all of these to epsilon max, then what will you get? And sum it. So what will we have? That if we sum all of these now, then it will certainly be less than n epsilon max, because now you are summing all epsilon max, so it will certainly be less than the original sum. Now let us take the logarithm on both sides. Let's do it by blue. Log of epsilon max over n. Okay. Let us first do the log and then we will divide by log of s max plus log of n. Now if we divide by n, we will have s epsilon max by n less than or equal to log s by n less than or equal to log s max by n plus log n by n. And now if you take the limit n tending to infinity, what we will get? This term will go to 0. And now we have log s over n bounded by the two same numbers. That means in the limit n tending to infinity, this log s over n has exactly the value s max over n. And that is phi max. So what we have seen, that this sum is actually, one can determine this sum just by the knowledge of the maximum value of the epsilon, or maximum value of the phi. And if some of you have know about, or some of you have read about the microcanonical or canonical ensemble thing, in microcanonical ensemble we have the energy at a particular state, at a particular energy state, and in canonical ensemble we have a distribution of energies. But from both of the theories we get the same results. And why that is? That is due to this theorem. Okay. Now let us do the continuous version. So let's say we have gas of molecules in a chamber, then the energy levels are not discrete, they have the continuous energy. then this epsilon will be continuous and the sum will convert it to an integration. So let us write it. So if we have a continuous distribution of epsilons, continuous distribution of epsilon i's, then sum will be changing to integration I dx exponential n phi x. This x may be energy or something else depending upon the situation. Now the picture will be, so there are many situations where these energy levels are actually continuous. So now the diagram will be something like this. We have x, some exponential x, so this is exponential n pi x, and it has a maxima at some value xm. Then we will see it is approximately equal to e to the power n phi x max, where the phi has a maximum value. Now this is, in mathematics it's called saddle point integration. So in saddle point the procedure is to expand phi around its maximum value. So expand phi around its maximum. By expanding near maximum, we will have I is equals to dx exponential n phi x max minus n phi prime x max, but this term will be 0 because phi has a maximum, so this term will be 0, and we will have n by 2 phi double x x minus xm whole square and so on. But since phi has a maximum, this phi double prime x is actually negative, and we can write it as this minus 1, put a modulus, okay, and there will be a third order term and so on. So let us write the third order term plus n over 6 phi triple prime x x minus xm whole cube. There will be fourth order x minus xm to the power 4 order term and higher order terms. Now first term is independent of x, so we can take it out of the integration. So we will have e to the power n phi x max integration dx exponential minus n phi double prime x modulus x minus xm whole square, other term e to the power minus or plus n by 6 phi triple prime x x minus xm whole cube and so on. Now if you this integration we know, if there are no other term we can know how to calculate it. It's a Gaussian and we can do it well, but since we have other terms, let us expand it. So e to the power n pi x max integration dx e to the power minus n pi double prime x minus xm whole square 1 plus n over 6 pi triple prime x minus xm cube, and there will be coming order of x minus xm to the power 4 term from other exponential if you multiply them all, and so on. So this integration is odd in x, and the potential or the in this function is even in n, so this term will be 0 because we are integrating from minus infinity to infinity. So our integration is minus infinity to infinity. So e to the power n pi x max minus infinity to infinity dx e to the power minus n pi x minus x square 1 plus order x minus xm to the power 4 times. And if you solve it, this will be of the order of 1 over n. Okay, let us elaborate this point. E to the power n pi x max integration minus infinity to infinity dx e to the power minus n pi prime x minus xm square plus minus infinity to infinity dx x minus xm to the power 4 e to the power minus n pi double prime x minus xm square, and so on. So this part is Gaussian, you can calculate it directly, and e to the power pi x max, let us write xm, and this will be pi, this will be 2 pi. So I guess I have missed 1 2 here, there is n by 2, yeah, so there is n by 2 here, yeah. So 2 pi n pi double prime m or x max plus, if you integrate this, so let us consider this as y. So this integration will be minus infinity to infinity dy y to the power 4 e to the power minus n pi double prime x by 2 x max by 2 y to the square, and if you solve it, this will of the order of root pi alpha not so let's say, yeah, so this will be of the order of n to the power 3 plus half. So we can take everything outside, and what we will have left as 2 pi n pi double prime xm 1 plus something of the order of n cube. So in the limit, yeah, but the question is there may be other maxima or other minima, other maximas are also there. But if you have done the same thing for other maximas also, let's say to the power n pi x m prime 2 pi n pi double prime xm prime, and so on. So let's say xm is xm and x minus this pi xm prime is, let's say, epsilon times, there is a difference of the order of epsilon. Then this term has, and let's say pi max xm is of the order of 1. So pi xm is, let's say, of the order of 1 minus epsilon. Then this term will have e to the power n, this term will have e to the power n minus n epsilon, which one can safely neglect in the limit n tending to 0, infinity. So other terms are always, can always be neglected comparative to the largest maxima. So what we have in the left hand side, integration e to the power n phi x max dx e to the power minus n by 2 pi double prime xm so we have 2 pi and pi double prime xm prime, we have solved it already, plus order of n cube. Now you take the limit, let us take the log. So you can see the importance of taking log here. You take the log n phi xm, so it is xm, yeah, n phi xm minus 1 over 2 ln n phi double xm 2 pi plus higher order terms. So let us divide by n now. So dividing by n and taking the limit n tending to infinity. What we will have? So this term will again be 0 in the limit n tending to infinity. So again we have limit n tending to infinity log I over n is pi of x max or xm. So you have seen this integration was like this, e to the power dx e to the power some n pi x, and now we can write it just as e to the power n pi x max. But okay, one thing is to note that there should be a dimension of x here, but if you write in logarithms there is no problem. So this whole integration can be evaluated by finding the maxima of this phi x. So this is the whole essence of the saddle point approximation. So if you sum or if you integrate large number of quantities which are exponentially dependent on n, and in the limit of n tending to infinity, the whole integration or the whole sum is just can be equivalent to if you evaluate the exponential at the maxima of the phi. So this is the saddle point integration method, and this is very important in statistical mechanics. These kind of calculation will be very frequently be encountered when you will do the partition function, averages, and so on. Now the last topic of this tutorial is the Stirling approximation. So the last topic is the Stirling approximation. In this, we will derive the logarithm of n factorial, how it can be simplified. The logarithm of n factorial in the limit n tending to infinity, how one can simplify it. So you can write the n factorial as 0 to infinity dx x to the power n e to the power minus x. You can just do it once here also. So let's say we have integration 0 to infinity dx e to the power minus alpha x, and it is what this is 1 by alpha. Now if you take first derivative, or let's say you are taking the nth derivative, you can do it sequentially also, but I am just doing it directly. Take the nth derivative, so we will have this dx x with respect to alpha, of course, then you will have x to the power, let's say capital N e to the power minus alpha x, and so yeah, so if you take the first derivative, you will have minus this side minus x, this side will have minus 1 over alpha square. Then if you take the second derivative, you will have x square. This in this part you will have so 1 and 2 by alpha square and so on. So this numerator have the form n factorial, and the minus factor cancels from both the sides, and this is alpha to the power n plus 1. So this you can check, so, and now set alpha is equals to 1, so you will have the same form as this. Okay, but this functional form is not same as the one which we have done earlier. So to put it in the previous form, we can write it as exponential phi x, where this phi x is n log x minus x. Okay, or equivalently one can write it as 0 to infinity dx e to the power n phi x, where phi x is now 1 over n log x minus x. Now we can use the saddle point approximation. So finding the maxima of this function, phi x prime will be 0. That means n over x minus 1 will be 0. It means it has a maxima at x is equals to 1. So we can expand it around about x is equals to n. So 0 to infinity dx e to the power n, so this 1 over n, so eventually this 1 over n will be cancelled out, so we don't have to worry much about this n factor outside. So n log n minus n, this is the value at phi at x is equals to n. Then first derivative will be 0, and second derivative 1 over 2 phi double prime x evaluated at n, and x minus over n, so x minus n square and other higher order terms. So phi double x prime will be, phi double x prime is this is 1. So we are taking just this function because we are not now taking n anymore. So n over x minus 1 and d by dx of this. So this is phi x phi double x is minus n over x square, and at x is equals to n, phi double x is minus 1 over n. Okay, so yeah, so there will be a plus sign now, and if you put the values, dx e to the power n log n minus n minus 1 over n x minus n whole square, this n factorial. Now just one can just do the integration. This term is not dependent on x, so it will be just outside of the integration, and this will be Gaussian by 2 pi n factorial. Now take the logarithm. Log n factorial is equals to n log n minus n plus 1 over 2 2 pi n, and so on. So in the limit n tending to infinity, log n factorial is approximately or equal to n log n minus n. This is the Stirling's approximation of n factorial. And this formula is actually very important in StatMath. You have seen also, maybe you have seen earlier, but if you not, you will see it. So this finishes this tutorial here. Thank you very much.